In this lecture, we are going to learn how to compute the Jordan normal form of a matrix. We will be proving the Jordan normal form theorem in the next lecture, and today we will assume that this theorem holds. Using this theorem, we will develop an algorithm for the computation of the Jordan normal form. The computations that we will be doing today will help us develop notations and intuition that will help us with the proof of the Jordan normal form theorem. Let us recall the statement of the Jordan normal form theorem. Let T be a linear operator on a space V, where V is a finite dimensional vector space over complex numbers. Then there exists a basis of V in which the matrix of T has a block diagonal form with the Jordan blocks on the diagonal. And the Jordan block looks like this. So we have a sequence of eigenvalues lambda on the diagonal. Then we have a sequence of ones parallel to it. And the rest of the entries are equal to 0. So in particular, this matrix is upper triangular. We have already proved the root decomposition theorem. Which says that in this setting, V can be written as the direct sum of root spaces u lambda 1 plus u lambda 2 plus u lambda k, where the root space u mu is defined as the union j goes from 1 to infinity of kernels of t minus mu I to the power of j. So this is the root space. We also saw that each root space is invariant with respect to our operator t. So we can view t as operator on each of these subspaces. Then it is clear that it is sufficient to prove the Jordan normal form theorem for each individual root space. So it is sufficient to prove the Jordan normal form theorem for the case when our vector space is a single root space, u mu. Let V be a non-zero vector in the root space u lambda. U lambda is the union of kernels of these operators. So we get that there exists an integer r such that t minus lambda I to the power r plus 1 acting on V is equal to 0, while t minus lambda I to the power r acting on V is not equal to 0. We give the following definition. A subspace spanned by vectors v t minus lambda I v, t minus lambda I squared v, and up to t minus lambda I to the power r v is called the cyclic subspace generated by vector v in u lambda. Let us prove the following lemma. Let v belong to u lambda and v is not equal to 0. Choose an integer r such that t minus lambda I to the power r plus 1 acting on v is equal to 0 vector, and t minus lambda I to the power r acting on v is not equal to 0. Then the set v t minus lambda I acting on v and so on t minus lambda I to the power r acting on v is linearly independent. Let's give a proof of this lemma. How do we prove that a set is linearly independent? We consider a linear combination of these vectors, which is equal to a 0 vector, and we need to prove that all coefficients of this linear combination are equal to 0. So let us form such a linear combination. So suppose the sum j goes from 0 to r, cj t minus lambda I to the power of j acting on v is equal to a 0 vector. We need to prove that all coefficients are equal to 0. We are going to reason by contradiction. And we are going to assume not all ci's are 0. Choose k to be the smallest index such that the coefficient ck is not equal to 0. So this means that all coefficients with lower indices than k are 0. Then this linear combination may be written in the following way. So we have the sum j goes from k to r, cj times t minus lambda I to the power of j acting on v and is equal to 0, with coefficient ck being non-zero. Now multiply both sides of this equality by t minus lambda I to the power of r minus k. Then we get the sum j goes from k to r, cj times t minus lambda I to the power r plus j minus k acting on a vector v is equal to a 0 vector. Here in the sum, j goes from k to r. So if j is strictly greater than k, then this exponent is r plus j minus k is greater or equal to r plus 1. And by assumption of our lemma, all these terms are automatically going to vanish. This tells us that in the sum, only the first term is possibly non-zero. So if we drop all the terms beyond the first one, then what will survive in this sum is the following. So we get ck times t minus lambda I, and when j is equal to k, so we get this to the power r acting on v is equal to a 0 vector. But by the assumption of the lemma, t minus lambda I to the power r acting on v is a non-zero vector. So thus, this equality implies that the coefficient ck is equal to 0. But this is a contradiction to our assumption. So we assume that ck was the non-zero coefficient. And the source of this contradiction was our assumption that not all ci's are equal to 0. And this proves that this set is linearly independent. Having proved that these vectors are linearly independent, we obtain that these vectors form a basis of a cyclic subspace. Only in this basis we are going to list these vectors in reverse. So we have v1 is t minus lambda I to the power r v. v2 is going to be t minus lambda I to the power r minus 1 v. vr minus 1 will be t minus lambda I v, and vr is going to be our vector v. Here we assume that t minus lambda I to the power r plus 1 v is equal to 0. Let us compute the action of t on these basis vectors. And we're going to note that t can be written as lambda I plus t minus lambda I. Then what is t acting on v1? So this is equal to lambda I applied to v1 plus t minus lambda I applied to v1. And let's recall what's v1. v1 is t minus lambda I to the power r acting on v. So the first term will give us lambda times v1, and the second term is equal to 0 because of this assumption. Now let us compute what is t acting on v2. So this will be lambda I acting on v2 plus t minus lambda I acting on v2, which is t minus lambda I to the power r minus 1 acting on v. And then the first term is equal to lambda times v2, and the second term is t minus lambda I to the power r acting on v. But that's the vector v1, so we get plus v1. Now, what is t acting on the vector v3? So this is lambda I acting on v3 plus t minus lambda I acting on v3, which is t minus lambda I to the power r minus 2 applied to v. And so this is lambda times v3 plus, and this vector is equal to v2. And so on. So when we apply t to the vector vr, so this is lambda I applied to vr plus t minus lambda I acting on vr, but vr is just v. And so what we get is we get lambda times vr plus vr minus 1. So what we see here is that this cyclic subspace is t invariant, because when we apply t to vectors from the cyclic subspace, we still remain within the cyclic subspace. And let us ask, what's the matrix of operator t when it acts on a cyclic subspace in this basis? The first basis vector is an eigenvector with eigenvalue lambda. So the first column is going to be lambda and then the column of zeros. When we act on the second vector, we get a lambda multiple of v2 plus v1. So the second column is going to be 1, lambda, and then the rest will be zeros. When we act on the third vector, we get lambda times the third vector plus the second vector. So the third column is going to be 0, 1, lambda, and then the rest will be 0. So what we see from the formulas is that the matrix of T acting on a cyclic subspace is the Jordan block. The Jordan normal form theorem claims that there exists a basis in which the matrix of T has Jordan blocks arranged along the diagonal. This can be reformulated in the following way. Since we observed that Jordan blocks correspond to cyclic subspaces, then we can state that every root space U lambda decomposes into a direct sum of cyclic subspaces. And each of these cyclic subspaces will produce the corresponding Jordan block. Now let us present a diagram for a cyclic subspace. Here on the top we have a vector that generates this cyclic subspace. We also denote this vector as VR. Then when we apply the operator t minus lambda I, we get vector VR minus 1, and so on. So when we apply this operator r times, we get the vector v1, which is t minus lambda I to the power r applied to vector v. But if we try to apply this operator one more time, so then t minus lambda I to the r plus 1 acting on v will become a 0 vector. So when we apply this operator one more time, then we kill the vector v1. To make our notation shorter, we introduce the notation of operator b, which is t minus lambda I. So when we apply the operator b, we descend in this diagram until we hit the ground level v1, and applying b one more time after that will produce a 0 vector. Now let us present a diagram for a typical root space. The Jordan normal form theorem says that each root space decomposes into a direct sum of cyclic subspaces. Equivalently, this says that a basis of the root space may be presented as a union of bases of cyclic subspaces. Each basis of a cyclic subspace we can represent by this strand, where down arrows represent the action of the operator b, which is t minus lambda I. When we hit vectors on the ground level with the action of operator b, we get 0. So this means that this ground level represents the kernel of the operator b, which is t minus lambda I. Next, let us ask the question: which vectors will belong to the kernel of b squared? And then we see from this diagram that b squared annihilate vectors on the first and the second level. So the kernel of b squared will be the span of vectors on the levels 1 and 2. Then the first 3 levels will represent the kernel of b cubed. The first 4 levels will be the kernel of b to the power 4, and in this case the whole space will be the kernel of b to the power 5. This reflects our definition of the root space u lambda. So we said that we consider the chain of kernels, so kernel of t minus lambda I that sits inside kernel of t minus lambda I squared, which sits in the kernel of t minus lambda I cubed, and so on. And the whole root space u lambda is the union, where j goes from 1 to infinity, of kernels of t minus lambda I to the power of j. Each of these strands corresponds to a Jordan block. So for this diagram, we have two Jordan blocks of size 5, one block of size 4, three blocks of size 2, and one block of size 1 by 1. So in the example with this diagram, the dimension of the root space is equal to 21. The vectors on the ground level form a basis of kernel of t minus lambda I. So this means that these vectors are in fact eigenvectors of t. And for this diagram, the dimension of the eigenspace is equal to the number of these strands, which is 7 in this case. So this is the dimension of the kernel of B. If we take the dimension of the kernel of B squared, then we need to add the 7 vectors on the ground level plus the 6 vectors on level 2. So we get that the nullity of B squared is equal to 13. Then the dimension of the kernel of B cubed will be 16, as it includes 3 additional vectors on level 3. And to get the nullity of B to the power 4, so we add 3 more vectors on level 4, so we get 19. And finally, so the kernel of B to the power 5 is our whole root space u lambda, and the dimension here, as we already said, is equal to 21. If we want to compute this basis for the operator t, then we need to identify the top vectors in each strand. Because once we have the top vector, we can compute all other vectors in the given strand by repeatedly applying operator b, which is t minus lambda I. Note that this is a picture for just one eigenvalue, and this kind of analysis needs to be done separately for each eigenvalue of operator t. Now let us discuss the algorithm for computing the Jordan normal form. So first thing that we say is that we want to find Jordan basis for each eigenvalue separately. Then we fix eigenvalue lambda and compute bases and dimensions of spaces kernel of b to the power j, where j goes from 1 to r and b is the operator t minus lambda I. How do we know when do we need to stop here? So that is, what is the value of r? We stop when dimension of the kernel of b to the power r is equal to algebraic multiplicity of the eigenvalue lambda. In order to compute the eigenvalues of operator t, we had to compute its characteristic polynomial. And thus, we would know the values of algebraic multiplicities for each eigenvalue. And the theorem on the root space decomposition told us that the dimension of each root space is equal to the algebraic multiplicity of the corresponding eigenvalue. Equivalently, this will tell us that at this step we will have a stabilization of our chain of kernel subspaces. So we will have that dimension of the kernel of b to the power r will be equal to the dimension of the kernel of b to the r plus 1. Once we get this stabilization, we know that we have covered the complete root space. Let us introduce notations for the vectors in our bases that we seek. The first index in each of our basis vectors will denote its level. So this vector sits on level 5, so we will call it v51. The second index will represent the strand. The vector down below from it will be called v41, then v31, v21, and finally the eigenvector here will be v11. Vectors in the second strand will be denoted v52, v42, v32, v22, and finally v12. Vectors in the third strand will be v43, v33, v23, and v13. Then we have vectors v24 and v14, then v25 and v15, v26 and v16. And finally, this eigenvector will be v17. These will be the notations for the basis vectors in these 7 strands. In order to compute these bases, we would want to begin with the very top. We would want to find the 2 vectors on the 5th layer. To do this, we consider the quotient space u lambda quotient by the kernel of b to the power 4. The kernel of b to the power 4 will be spanned by all the vectors up to the 4th layer. So this quotient will have as a basis the equivalence classes of vectors v51 and v52. This will give us these 2 vectors on the top that we seek. Computationally, we are doing the following procedure. We want to complete a basis of the kernel of b to the power 4 to a basis of the space u lambda, which is the kernel of b to the power 5. Now, the subspace kernel b to the power 4 has dimension 19 in this example, and the kernel of b to the power 5 has dimension 21. So when we complete a basis of a 19-dimensional space to a basis of 21-dimensional space, we get 2 extra vectors. So this gives us vectors v51 and v52. These are the 2 extra vectors that complete the basis of kernel of b to the power 4 to the basis of u lambda. Once we have these 2 top vectors, then we compute the vectors in the first 2 strands. So v41 will be b applied to v51, v31 will be b applied to v41, and so on. And the same for the second family. So we will have that v42 is b applied to v52, and so on. So basically, we are descending in these strands by applying iteratively operator b to the top vectors. Once we complete this step, we will get 10 vectors in the first two strands. As our next step, we want to identify the top vector in the third strand. To do this, we consider the following quotient space. Let us take the kernel of b to the power 4 quotient by the kernel of b cubed. This quotient space has the following bases. These will be equivalence classes of the vectors that sit at level 4. So these will be equivalence classes of v for 1, v for 2, and v for 3. The first two vectors we will already have computed from the first two strands, and it's only the third vector that we seek. And to find the top vector on the third strand, we take a basis of the kernel of b cubed together with vectors v for 1 and v for 2, which we already have, and complete to a basis of the kernel of b to the power 4. Here, the kernel of b cubed has dimension 16 plus 2 more vectors. This will give us an 18-dimensional space. And we're completing this to a basis of a 19-dimensional space. So this gives us one extra vector. And this vector will be v for 3. And once we have v for 3, so we compute all other vectors in the third strand by iteratively applying operator b to the top vector. So we will get v33 is equal to b applied to v43, then v23 is b applied to v33, and finally v13 is b applied to v23. And if we apply operator b to v13, then we are guaranteed to get 0. It is often useful to make this verification just to make sure that our computations are correct. Now we see that in this diagram we have no strands of length 3. So this tells us that we should proceed to finding the top vectors on level 2. To find the top vectors on level 2, we take a basis of the kernel of b, which represents all the vectors on level 1, together with the vectors on level 2 that we have already computed. So these are vectors v21, v22, and v23. And complete this set to a basis of the kernel of b squared. Now, the kernel of b here is 7-dimensional. Then we add 3 more vectors, we get a 10-dimensional subspace. And the kernel of b squared is a 13-dimensional subspace. So this will give us 3 extra vectors. So this will give us vectors v24, v25, and v26. Having computed these vectors, we just descend down in these strands. Then we compute vectors v14 has B applied to V24, V15 has B applied to V25, and V16 as B applied to V26. And finally, we would only need to find the vector V17 on level 1. Here, we don't need to work with quotient spaces, and we just complete the set of vectors that we already have on the ground level. So from V11 to V16 to a basis of the kernel of B. The kernel of B in this example is 7-dimensional, and we already have 6 vectors in it, so this will give us 1 extra vector. So this will produce the vector V17. We see that in order to carry out these computations, we will need to know this diagram, which will guide us through the process. If we just know the matrix of B, how do we uncover the structure of the diagram? What we have done is we have computed the dimensions of the kernels of B, B squared, and so on. Well, for this example, we know that dimension of the kernel of B is 7. The dimension of the kernel of B squared is 13. The dimension of the kernel of B cubed is 16. Dimension of the kernel of B to the power 4 is 19. And finally, dimension of the kernel of B to the power 5 is 21. So we have computed this increasing sequence of numbers. Now, what these numbers tell us? These numbers tells us that we have 7 vectors on level 1. Then the number of vectors on level 2 is the difference between the kernel of B squared, which includes vectors that are both on level 1 and level 2, minus the dimension of the kernel of B. So this means that the number of vectors on level 2 is the difference 13 minus 7, which is 6. And then the number of vectors on level 3 is the difference of the dimension of the kernel of B cubed minus the dimension of the kernel of B squared, which is 16 minus 13. So this gives us 3 vectors on level 3. Then the number of vectors on level 4 is 19 minus the previous number, 16, which is 3. And finally, the number of vectors on the top level, level 5, is 21 minus 19, which is 2. And once we have the number of vectors on each level, then we can easily recover this diagram. So this 2 is the number of strands of length 5. Then the number of strands of length 4 is equal to 3 minus 2, which is 1. Then from here we get that the number of strands of length 3 is equal to 3 minus the previous number, which is also 3. So we get 0, and so on. In this way, we are going to obtain this basis, and then we place all these basis vectors to form the change of basis matrix. So we form a change of basis matrix C by placing basis vectors as columns. We need to put these basis vectors in the proper order, and in each strand we should start with the basis vector, which is a vector at the bottom. So we will start with v11, then we have v21, v31, v41, v51. So these are the vectors in the first strand. Then we start with the eigenvector of the second strand. We take v12, v22, and so on. By listing vectors in each strand starting from the bottom, we will obtain this change of basis matrix. And then we form the Jordan normal form matrix J by arranging Jordan blocks of appropriate sizes along the diagonal. So here our first strand had length 5. So this means that first we put a 5 by 5 Jordan block with eigenvalue lambda on the diagonal. The next Jordan block also will have size 5 by 5. Then we place a 4 by 4 Jordan blocks, then 3 2 by 2 Jordan blocks, and finally we will place a 1 by 1 Jordan block, which is just eigenvalue lambda on the diagonal. And we carry out this procedure for each of our root spaces. So this means that combining all these calculations together. And finally, we apply the change of basis formula. The matrix of T in the standard basis is equal to the product of the following three matrices, where we have the change of basis from standard basis to basis B, then we have matrix of T in basis B, and then we change the basis from B to the standard basis E. If the matrix of T in the standard basis is matrix A, then here we get the following relation between the original matrix and its Jordan normal form. So we'll have that A is equal to change of basis matrix C, which we constructed here, times the Jordan normal form matrix J that we constructed here, times C inverse. This becomes the Jordan normal form generalization of the diagonalization formula. Now let us go over two examples where we bring a matrix to the Jordan normal form. In our first example, we consider the following 4 by 4 matrix, which we want to bring to the Jordan normal form. One can compute the characteristic polynomial of this matrix, and to save time, I'm just going to write it down. So this characteristic polynomial is lambda plus 1 times lambda plus 2 cubed. This means that this matrix has two eigenvalues. Lambda 1 is equal to -1, and lambda 2 is equal to -2. As long as the characteristic polynomial has a factorization into linear factors over real numbers with real roots, we can bring a real matrix to the Jordan normal form without having to go to complex numbers. Here, our four-dimensional vector space will decompose in the direct sum of the two root spaces. We will have a lambda 1 equals -1 root space, and the second root space corresponds to the eigenvalue -2. The dimensions of root spaces are given by the algebraic multiplicities of the eigenvalues as the roots of the characteristic polynomial. So this tells us that the root space that corresponds to lambda 1 equals -1 has dimension 1, and the root space that corresponds to lambda 2, which is -2, is equal to 3. When constructing the Jordan basis, we're going to treat the eigenvalues separately. One basis vector will come from the root space of lambda 1, and 3 basis vectors will come from the root space of lambda 2. Let's look at the case of lambda 1, which is -1. Here we have to consider the matrix A plus I and compute its null space. If we bring the matrix A plus I to reduced row echelon form, we will get the following matrix. The rank of reduced row echelon form is equal to 3, and the nullity is equal to 1, as expected. Since the dimension of the root space is equal to 1, we also can say that dimension of the eigenspace will also be equal to 1. Let us find the lambda equals -1 eigenvector for our matrix A. To describe the null space of this matrix, we see that x4 is a free variable, so we say x4 is equal to t. Then from the last equation we get that x3 is equal to t, then x2 is equal to 0, and x1 is equal to t. So we see that the eigenvalue here, u1, is the following vector. It's 1, 0, 1, 1. This is lambda 1 equals -1 eigenvector of A. When computing eigenvectors, it's very easy to verify that the answer is correct. So we just multiply this vector by matrix A, and we should get the opposite of this vector. This completes the calculations that we need to carry out for the first root space. Let us consider the matrix A plus 2i and bring it to reduced row echelon form. To save time, I skipped the calculations, and so here is the answer. So this will be the reduced row echelon form of A plus 2i. The rank of this matrix is equal to 3, and the nullity is equal to 1. This means that matrix A has a single eigenvector with the lambda equals -2. This tells us that we have the following diagram for lambda 2 equals -2. So we will have a single strand because we have one eigenvector, and so it will have length 3 because the dimension of the root space is equal to 3. To construct our basis, we need to get to the vector on the top. This vector will belong to the space the kernel of B cubed. So this is the space that we need to compute. So here B is A plus 2i. This is our matrix B here. And if we compute B squared, we get this matrix. Its reduced row echelon form is written down on the right. The rank of the matrix B squared is equal to 2, and the nullity is also equal to 2, which agrees with the information from this diagram. Let us describe the null space of B squared. So here the free variables are x2 and x4. So we say x2 is s, x4 is t, then x3 is equal to 0, and x1 is equal to s plus t. And we get the following bases of the kernel of B squared. We get two vectors, one that corresponds to s parameter and one that corresponds to t parameter. So this will be 1, 1, 0, 0 and 1, 0, 0, 1. Next, we consider the matrix B cubed, which we see is the matrix of rank 1. So this is its reduced row echelon form, and this matrix will have a three-dimensional null space, which is the whole root space that corresponds to lambda equals to -2. Let us describe this null space. So here the free variables are x2, x3, and x4, and we assign parameters r, s, and t. And from the first equation, x1 will be equal to r minus s plus t. This gives us the basis of the kernel of b cubed, which is equal to the root space lambda 2 equals to -2. Here we have three vectors. The first vector corresponds to parameter r. It will be 1, 1, 0, 0. The second vector will correspond to parameter s, -1, 0, 1, 0. And the last vector will correspond to parameter t. So this will be 1, 0, 0, 1. To get the vector on the top of this strand, we need to complete a basis of the kernel of b squared, which is this subspace that consists of the bottom two layers, to a basis of the kernel of b cubed. In general, to do this, we would have to form a matrix where we first place basis vectors of the kernel of b squared, and then extend it by placing the vectors from the kernel of b cubed. And then we do row reduction. In this particular situation, we've got lucky because the vectors from the basis of the kernel of b squared happen to be present in the basis of the kernel of b cubed. If we label the vectors in this diagram as w3, w2, and w1, then we see that as the top vector w3, we can choose this vector from the basis of the kernel of b cubed, -1, 0, 1, 0, because the other two vectors form the basis of b squared. Finally, we compute vectors w2 and w1 by going down the strand and applying the transformation b. So we get that w2 is equal to matrix b applied to w3. This will give us vector -1, 1, 0, -2. And we can see that this vector is indeed a linear combination of the two basis vectors of the kernel of b squared. And finally, w1 is b applied to w2. This will give us the vector w1, which is 0, 1, 0, -1. And we can see from this reduced row echelon form of the matrix B that this is indeed the eigenvector for the matrix A with eigenvalue lambda equals -2. The basis that we're going to use is the following. So we'll take the vector u1, which is the basis vector for the root space corresponding to lambda equals -1. And then the basis for the root space that corresponds to lambda equals to -2. So this will be w1, w2, and w3. By placing the coordinates of these vectors as columns, we'll get the change of basis matrix. So the matrix C is the following. So first we place u1, which is 1, 0, 1, 1. Then we place w1, 0, 1, 0, -1. Then we place w2, -1, 1, 0, -2. And finally, we place w3, which is this vector here, -1, 0, 1, 0. And we write the Jordan normal form matrix. So here in the top left corner, we'll have a 1 by 1 Jordan blocks that corresponds to lambda equals -1. So here we'll have -1. And then we have a 3 by 3 Jordan block that corresponds to lambda equals to -2. So we'll have -2, -2, -2, and 1 here and 1 here. And the rest of the entries are 0. Here we can see the block structure. So we have a 1 by 1 block and a 3 by 3 block. What we could have done differently is to place strands in different order in this basis. So here we have two strands, and we could have placed w vectors first and u1 as the last vector in this basis. This would mean that this 3 by 3 block will be written first, and then 1 by 1 block will be written in the bottom right corner. Finally, we write down the change of basis formula, that A is equal to C times J times C inverse. And by computing the product in the right-hand side, we can verify that the result will give us indeed the original matrix A. Let us go over one more example when we bring a 4 by 4 matrix to the Jordan normal form. Let us consider the following 4 by 4 matrix, and its characteristic polynomial can be computed and is equal to the polynomial lambda plus 1 to the power of 4. This means that we have lambda equals minus 1 is the single eigenvalue, and the corresponding root space is the whole space of dimension 4. To find the Jordan basis of this root space, we consider the matrix A plus I, which is our matrix B. Matrix A plus I has the following reduced row echelon form. From this reduced form, we see that the rank of this matrix is equal to 2, and so nullity is also equal to 2. So we conclude that the dimension of the kernel of B is equal to 2. So this tells us that in our Jordan basis we have two strands, because we have two eigenvectors. Let us compute the basis of the kernel of B. Here we see that we have two free variables, x3 and x4. So we say x3 is s, x4 is t, and then we see that x2 is equal to t and x1 is equal to t. So we get basis of the kernel of B consists of two vectors, 1, 1, 0, 1. So this is the vector that corresponds to t parameter, and 0, 0, 1, 0. This is a vector that corresponds to S. Next, we need to calculate what is the matrix B squared. And if we do this, we see that this matrix will be completely 0. This tells us that the dimension of the kernel of B squared is equal to 4. And then we can see what is our diagram here. So here we see that we have two strands, so that is two eigenvectors at the bottom, and everything lies within the first two layers. So the only possible diagram is the following. So we have two strands of length 2, which corresponds to two Jordan blocks of size 2 by 2. Let us label the vectors here. We have v21. Down at the bottom we have v11. This vector is v22. And at the bottom here we have v12. To determine top vectors v21 and v22, we complete a basis of the kernel of B to a basis of the kernel of B squared, which is the whole space V. For this, we place the basis vectors of the kernel of B as columns. So we have 1, 1, 0, 1, and 0, 0, 1, 0. And then we extend this with the standard basis of the four-dimensional space. So we have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. We can easily compute the reduced row echelon form of this matrix and see that we have pivots in the first four columns. So this means that the first 4 columns of this matrix will form a basis of R4. So we have a basis of V that consists of these 2 vectors here, 1, 1, 0, 1, 0, 0, 1, 0, and the 2 first standard basis vectors, E1 and E2. So 1, 0, 0, 0, and 0, 1, 0, 0. This tells us that as our top vectors, we can choose E1 and E2. So our vector V21 is going to be the vector 1, 0, 0, 0, and the vector V22 is the vector 0, 1, 0, 0. Now we can determine the bottom vectors by just going down these diagrams, applying operator B. So what we get is that the vector V11 is equal to B times E1. So this is the first column of the matrix B. So this is the vector 1, 1, minus 2, 1. And the vector V12 is B applied to E2. So this is the second column of matrix B, which is 0, 0, 1, 0. And now we have the Jordan basis. Now in this basis we start listing vectors starting with an eigenvector. So we have V11 and V21, and then V12 and V22. Now we get the change of basis matrix by placing coordinates of these vectors as columns. So V11 is 1, 1, minus 2, 1. V21 is the vector E1. We have 1, 0, 0, 0. Then V12 is the vector 0, 0, 1, 0. And V22 is the vector 0, 1, 0, 0. So this is our change of basis matrix. And the Jordan normal form matrix, it consists of 2 2x2 blocks that correspond to the eigenvalue -1. So we have -1 along the diagonal, and we have 1 here and 1 here, and 0 elsewhere. And finally, we write down the change of basis formula, that our original matrix A is related to these matrices C and J in the following way. A is equal to C times J times C inverse.